Test, let me just announce, test 2 will be on Wednesday, November 3rd, and it will be live, and there will be 2 proctors present in Marshak room 3, and they will check you in so that each one who enters, you have to sign in to prove that you are there, because Blackboard somehow does not distinguish people when I say blah blah blah. Anyway, so the proctors will check you in, and I will not start the Blackboard exam till you have been checked in and settled. So I allow about 10 minutes, because somebody has to go around, and then you have to be spaced at least 2 seats apart, and then you have to be seated in a column so that you know you cannot look sideways into your friend. So it has to be in a column. Anyway, so the exam, Blackboard exam, will start at around 5:10, and it will be for 75 minutes, an hour and 15 minutes. And there will be 15 questions. And I'm still sort of fine-tuning the questions. And the questions will cover, let me just get the actual chapters 21, 22, 24, and 25. All right, you got it. It's 21, 22, 24, and 25. And the questions will again be in blocks. And within each block, there may be, I don't know, 2 multiple answers and 2 calculated formulas, or 3 multiple answers, 1 calculated formula. I don't know, but they will be all with respect to a particular area involving, let's say, electromagnetic EMF. And you need to then, you yourself will know, oh, for motional EMF, these are the formulas. And you also know what it means. Whatever symbols there are, you know what it means, and therefore you know how to use it for the particular question. All right? And there is no backtracking. You have 2 attempts, and each attempt is again itself randomized. When you do a particular random block, the order may be a little bit not what I would have. I would have said, first look at A, then look at B, then look at C. But Blackboard just randomizes everything, including inside the block. So what you have to do is you keep your own notes so that you know this one is, I don't know, with respect to reflection of something or other, or it has to do with, I don't know, transformer. And you then say, okay, I have these formulas, basic formulas, and then this question is asking about whatever is the output current, or this one is asking about whatever is the output voltage. Well, you keep your own notes, and you then answer it with the warning. With each block, I will say there are 2 multiple answers and 2 calculated formulas, so you know that they are, you anticipate that then another question that has to do with actually calculation involving some formulas. Or this one is first, you got calculated formulas, you have already used it, but then the next one says, what was the formula you used? So you know what's the formula you use. All right. I'm sorry, but being Blackboard, there's no way I can ask it to do it with A, B, C in a given order. Okay. Any questions? All right. If not, then let's continue with chapter 26, which has to do with reflections. We already had internal reflection, and I downloaded this from, I think this must be from Giancoli, on total internal reflection, on the interesting, again, this is something that, what did you say? What was that now? Somebody say it out loud. What did you ask? Yeah, there are 15 questions, right? In other words, you get 5 minutes per question. And my advice is look at it carefully. You have time. 5 minutes means 900 seconds, right? There's 60 seconds per minute. So take your time, read it carefully, and watch out for the units. Sometimes there's this milli this, nano this, micro this, and so on, which is 10 to the power of -6 for micro and so on. Just be aware of that, because when you apply the formula, these conversion factors are important. And then you just have to say, what is the concept here? Is this talking about, I don't know, a force on the wire due to the external magnetic field? If it is, then I know there's one formula I forgot. You look it up. Or is this about what? There's this Michael Faraday, that very famous guy. Something about his law, and some Supreme Court enacted his law, whatever. Well, if you say it is Faraday's law, you know what formula it is, and then you say, gee, I know. They told me enough about what is the flux. If they told you enough what is about the flux, then you know something about the rate of change of the flux, and therefore you know what is the induced EMF, right? So you need to ask yourself, what is the concept involved? And then you have to use your algebra. You have to use your trigonometry, because after all, sometimes these crazy questions have a certain angle, sine theta, cosine theta, whatever, I don't even know. So you have to then say, I now know what concept, and then I will just use algebra to figure out what you want to ask me. Okay? All right? So now let's settle back and come to chapter 20. This is 26. We now have already understood about total internal reflection, which is the progression beyond just simply Snell's law. Snell's law already says that if I have my incident ray, on the particular interface, let's say I'm under the water and I am now looking up, well, the light ray that is coming up, or the light ray that I now follow, the light ray, when it comes to the interface, there's a certain angle. Let's call that, I don't know, sometimes the book calls it N1, sometimes it's called N2, but anyway, there's a certain angles. Now, when it now comes out, Snell's law says, the light ray will be bent away from the normal, because this water is denser medium than the air. Well, as you now increase the angle of incidence, if you are now looking further away from you, you're under the water scuba diving, and you're looking further away from you, the angle of incidence at the surface of the water is now larger. Then Snell's law says, the transmitted, refracted ray outside the water surface will now be even greater. But then it cannot be greater than 90 degrees out there. Therefore, there is what is called the critical angle. When you now look at the surface further away than this cone, there's a certain cone which works out to be 49 degrees for water. So if you now look at from under the water, you look at some point that is even further away outside this cone of 49 degrees, the ray coming to this interface, the angle of incidence now is now greater than 49 degrees. And then Snell's law says, I give up. Snell's law says, I have no idea what you must do. Meaning there is no refracted ray. If there's no refracted ray, all of it is totally internally reflected. And the application is when you're scuba diving, that outside this cone, what you see is not the sky above you. What you see instead is the ocean bed in front of you. All right. So this picture says, oh, very clear. Therefore, I know I am looking upward. If I look straight up, oh, I see my friend still saying hi to me, and I see the palm tree. But then around it, I see sand. I see the ocean floor. Now, there is then a warning. I'm not a scuba diver. Anybody a scuba diver? I forgot to ask. Did I ask last time? Anybody who is a scuba diver? Yes or no? I'm trying to engage you, but nobody is answering. Do you know what is a scuba? Nobody knows what is a scuba, so therefore you don't know what is a scuba diver. Yeah. If ever you become, let's say, you have a career, you now have enough money, and there are people who want to go, you know, have some relaxation. There are people who like to dive and explore, you know, some coral reefs. And I know of some friends who fly all the way to the Great Barrier Reef in Australia and elsewhere in order to explore. And now the warning, it's a good thing to remember. When you're doing scuba diving, you're not just going around the swimming pool, you're going maybe 2 miles, 3 miles down, and you have a scuba tank that is sufficient for you. Yes. Now, when you're going scuba diving, you're going far. Your original starting position is where your boat is. You came, down here, and then you are swimming, and now you are going, looking further and further away. Well, the weather over this part of the coral reef, which may be 2 miles away, may be beautiful sun, but instead there's a thundercloud over you. But then when you look far away, because that's your whole purpose, you flew all the way to Australia in order to explore those coral reef, right? Great Barrier Reef. You are so interested in what's out there 2 miles away. Oh, 2 miles away, oh, the weather is nice. So then what you see is blue. You remember like the mirage of the desert? What you see is blue. You did not look back up to say, oh, over there, on my original starting point, it may be rainy, it may be thundering, and you don't hear the thunder when you're down in the water. Just beware. What you see beyond this cone is not what is above you. What you see beyond the cone is what is actually down, on the ocean floor ahead of you, far away from you. Okay, I may have. All right. Now, fiber optics also is something that takes advantage of this total internal reflection. And we already saw that. And this is a good picture because as your doctor want to look at things, well, for endoscopy and so on, they are using fiber optics. All right. Now I can go on. Now we want to come to prisms and rainbows. And that's a very interesting subject. And just for historical note, Isaac Newton, apart from postulating the law of universal law of gravitation, was very much interested in the prism and was interested in this behavior of light. Well, a prism is made of glass, glass, and you have your light that comes in. And of course, we already know Snell's law that when you have incident light, when it enters the prism, it will be refracted, bent towards the normal. So if this is the original angle of incidence, right? You see this? If this is the original angle of incidence, it will now have a smaller angle of refraction. So therefore, it will now be bent like as if it's going parallel to the ground, whereas here it was going upward. It's parallel to the ground. But then when it comes to this side of the prism, now it's going to come out from a dense medium to a rarer medium, and therefore the ray would be bent away from the normal. And so what happens is your light ray that was going up will now be bent downward. All right, so this is simply making use of the Snell's law. But what Newton discovered, I mean, actually, this was already known before Newton. It's just that Newton tried to put a more scientific angle, right? Well, what you find is if you send light, which you would have said is ordinarily white light, the light that now comes from the sky appears to me like white light. It's not like during sunset, it becomes orange, right? So I have now, let's say, white light, quotation mark white. But by the time you let it go through the prism, there seems to be a color that is produced by the prism. And in ancient days, they probably thought of it as, oh, prism has this ability to produce color. And what happens is you will get now red and yellow, orange, red, orange, yellow, green, blue, violet. You will have a range of colors, and the scientists have figured out or measured, and that in itself is an interesting thing, to be able to measure we already learned that in electromagnetic waves, that the red light has a longer wavelength than violet, and particular is about 700 nanometers. Well, this one is more precise, 660 and 410. All right, so what is the, let's say, the underlying reason why there's a separation? And that comes to this thing about index of refraction being dependent on the wavelength. The index of refraction for red light is different than the index of refraction for blue light, for orange light. And it is because it is different that they now come out at different angles. And we will see that. This is then trying to figure out why is there now a color coming out of prism. Until you have this concept of index of refraction, it was not possible to understand. So all you say is, gee, I have this prism, just like I have a diamond, ring. Oh, it is sparkling. Well, so you can say that a prism somehow is able to produce color. What happens really is that now we come to this concept that the index of refraction depends on the wavelength. And now the scientists have actually measured it. They have done a lot of experiments from the angle and so on to then discover that for red light, the index of refraction is, let what this says is 1.52, whereas for violet light, the index of refraction is 1.538. That means that when you have red light, it is bent less. But when you have a violet light, it is bent more. Do you see? That's what this index of refraction is. It has been bent more. So because it's been bent more, it will arrive here with a bigger angle. And now it will be bent away from, it will be bent more towards the normal. It will be bent more away from the normal. So it will now come out at a bigger angle than for red light. Do you follow this progression? That the first incidence, first refraction, the violet light is bent more towards the normal, whereas the red light is bent less towards the normal. Then when you now come out, the red light is bent less away from the normal, but the violet light is bent more away from the normal. So therefore it comes out at a more sharper angle. So this is how then you get a rainbow from a prism, a rainbow of colors. Are you following this?
Yes, Professor.
Okay, good. Thank you. And now, the refraction of light depends on the index of refraction. So the concept question, I mean, this is the book now telling you, is it or it is possible for a prism to bend light upward, downward, not at all. And what they want to ask is, could this be possible? We just showed before that indeed it's bent away, so it's sort of bent downward. But here they say, could it be possible that I have the same prism? I mean, the prism hasn't changed, but I put it in some environment, you know, uh, not in the lab, but somewhere in some other environment where I have an incident ray, and now each time it is, instead of being bent downward, it's bent upward. And so they say, could it be possible? But when I first saw this figure, I say, impossible. And then I realized that they are very tricky. That's why I say sometimes the Wiley Plus, they give you things that you have to first sit back and say, no, I better read it more carefully. They say it is possible. So then how can it be possible? All right. They say it is possible. I give you a certain environment where this happens. Then you just say, how can I arrange it? Well, oh, and then this other way. But let me look at this one. So first, N1 now, let's use the notation which they use. Let N1 refer to this medium, this yellow medium. I don't even know what medium it is. Maybe it is a particular kind of liquid whose index of refraction is something, all right? And now, for this to be the case that they want, this medium, index of refraction of this medium must be greater than the index of refraction of glass. The picture we had earlier, was air. And then I have light coming in from air into the glass prism. But now they are basically saying, what if I don't fill it with air? I fill it with, I don't know, methane or something, some denser, uh, you know, gas or something, whose N1 is greater than your glass. I don't even know. I'm not You have to look up the table. The scientists will have the table for the index of refraction for various kinds of fluids, for various kinds of medium, right? And if N1 is indeed greater than N2, then what happens is you will have this one going upward. All right. And now the other one, they say, is it possible that indeed it didn't get deviated at all? It went straight through. Is it possible? Well, if indeed this itself is glass, if this itself is glass, the N1 and N2 are the same. Therefore, index of refraction, I mean, N1 and N2 have the same index of refraction. Sine theta 1 must be therefore sine theta 2. Therefore, it just goes straight through. There's no deviation. So this is the kind of value plus concept questions that they like to knock you over the head with, all right? And just between you and me, I don't think I will ask you that in the blackboard exam, okay? Cheer up. But this is just to show you what the book sometimes does, to wake you up. But what is more important for us in our daily life is that we always enjoy a rainbow. We always enjoy a rainbow. There's no rainbow now, but there are times when you can actually see a rainbow over Manhattan. You can see a rainbow over George Washington Bridge. I guess you don't ever look out, do you? Now, one thing which we can ask before we even go further. If you want to look for a rainbow, which way do you look? To the east, to the west? You've never tried to look at the rainbow?
Yes, but whatever the rainbow is, that's where we look at.
And then you say, ah, there's a rainbow, beautiful. But now my question is, you are actually trying to look for the rainbow. Which direction should you look? Let's say it is a setting sun. I don't know which way your house is, right? Let's say it's the setting sun. Which way should you look? Should you look towards the sun for the rainbow? Or do you look away from the sun for the rainbow? Somebody said what?
I guess towards the source, like towards the
Toward the
water.
source? Uh-huh. Well, no. As I said, it is the setting sun. So let's say that is the west, right? Do you look to the west setting sun and say, hey, where's the rainbow? Is that the place, direction you look when it is a setting sun? Or do you now say, oh, the sun is setting there. Let me look this way and see if there's a rainbow. You've never tried that? I
Opposite
mean,
to the sun?
huh? Away from the sun. You look away from the sun, and if there is a lot of water vapor in the air, namely after some kind of rain or something, you will then see the rainbow. All right? I mean, these are, things that apply to our daily life, especially when you want to enjoy, some peace and you want to now look at what, there is out there instead of being well worried about the exam, about this or that. It is good to remember you want to look for the rainbow. Don't look towards the source, the sun. Instead, you look away from the source. And then, if there is enough water vapor, you will see a rainbow. Okay, so now that we have sort of appreciated, we now become like a physics. After all, this is a general physics course, and say, what caused a rainbow to occur? Well, you need, of course, sunlight, and the sun has to be on this side. Now you look towards away from the source, and you need water vapor, a lot of water droplets. If there hasn't been any rain and the air is dry, sorry, there's no rainbow. You cannot see the rainbow. But if there has been a shower, or if there has been enough water vapor in the air, water droplets, then one drop here, a single drop, if sunlight approaches it, it will of course be bent towards the normal, so it will be bent downward. But now, if it is bent just at the right angle, it could then be totally internally reflected, right? It depends on your angle of incidence. So we will then know there's a certain angle at which you will see the rainbow. But anyway, when they are of a certain angle, at a certain angle, then when it's been bent, right? When it's been bent to the normal, it now arrives at the opposite side of the droplet, and the angle now is greater than the critical angle. For water vapor, I forget now. Then we have the critical angle for water. I forgot what was the critical angle. And then it will then be totally internally reflected. But then when it comes here, it will now be bent away from the normal because now it comes out. And the thing is that red light is bent less, whereas violet light is bent more. So violet light is now bent and reaches this part of the water droplet, and when it comes out, it will be bent away more. So it will be bent like relative to this one is like upward. That's why when you have light, sunlight coming in, it will now be totally internally reflected, and now the refracted ray out would have red light at a steeper angle with respect to the horizontal than violet. Are you following? It's sort of like you are now like Newton. You are interested in how the red and the violet light emerge from some prism, except that this is not the prism anymore. This is a water droplet. Newton was not sophisticated enough to have water droplets inside his lab, but a prism is easy. You just buy a prism and you can now study it. So here, this is one where you have sunlight and you now have one total internal reflection, and red light comes out at a bigger angle respect to horizontal, because after all, we are on the ground. What we see is here. So what we see is red light comes in at the higher angle, whereas violet light comes in at the lower angle, smaller angle relative to the horizontal. Okay, do you see now this picture? You enjoy nature by looking over here, but you're trying to figure out what is the reason why you have this rainbow with the kind of spread of colors. All right. Yeah, it's because of the different wavelength. The red light has a longer wavelength than violet. And index of refraction depends on your wavelength. So having, let's say, understood this, we can let's say, yeah, now I get the concept that because because of the fact that the red light has a longer wavelength, it is now bent less in the refraction. The index of refraction is smaller. So it will now emerge at a steeper angle with respect to the horizontal than the violet. And we now then see you are here. The sun is to your back. You see, you notice? You are looking this way. The sun is behind you. The sun shines the light, and you have a lot of water vapor in the air. And these water droplets, whether they are this one, this one, this one, all over, they all will send the red light coming in at a steeper angle than the violet light. Therefore, what you see is red is on top of the rainbow and violet is at the lower end of the rainbow. Okay? All right? I mean, the main thing is you at least say, yes, it makes sense. And the actual angle, well, then somebody has to work out the geometry of this and so on and so forth. But for rainbow, the experts have already worked it out. Now you can look it up. Some angle, I forgot now, whether it's 40 something, 50 some, around 50 or 40 something. Okay, good. Now, this is what is called, here you have, right? This is not in Wiley Plus. I downloaded it somewhere. It's a much bigger picture. You have the raindrops and you have the sunlight, and this has one internal reflection. This has one internal reflection, and the red light now is at a steeper angle. What is this? 42 degrees, and the other one is 40 degrees. So you see red light at the top of the rainbow. This is one internal reflection, all right? Okay, that's primary rainbow. And this is Roy Gibb. Red, orange, yellow, green, indigo, violet. Roy Gibb. I don't know whether you have remembered it as Roy Gibb or Vibgyor. Violet, indigo, green, violet, blue, green, yellow, orange, red is Vibgyor, or you read it as Roy Gibb. So anyway, that's the way to remember the order of the color in a rainbow. But have you ever seen a secondary rainbow? Have you? Primary rainbow is very easy to see, assuming that there has been some showers or something, rainstorm. Afterwards, if the sun is just the right angle, you can see a rainbow. You have seen a primary rainbow, but have you ever seen a secondary rainbow? I know. It's not easy. Part of the or actually most of the reason is the secondary rainbow is higher, and it requires two double internal reflection, and so the intensity of light that reaches you is less. So usually primary rainbow is very bright, you can see it, but secondary rainbow is sort of fainter, not faint, but not so bright, and it is higher, and generally there are more clouds or something that make it not easy to see. So primary rainbow, you see it all the time, but secondary rainbow, it's not as easily seen, especially if you're in Manhattan. All the buildings will block you. So here is a picture of primary rainbow and what is a secondary rainbow. And you notice that primary rainbow is one internal reflection. This is the sunlight. It comes in, it gets reflected totally internally once and comes out. So you get the red and you get the violet. But now, for those raindrops that are higher, so these raindrops are closer to the ground. For raindrops that are higher, what happens is the sunlight still comes in at the same parallel to this. the sunlight is just coming in. They are all in this direction, let us say. Then when they enter the raindrops that are further up, they get now totally internally reflected twice. You see, the angle of its incidence, because it is now reaching the lower part of the raindrop, when it goes in, it now hits this at a big internal angle. Therefore, it's internally reflected. And then when it is reflected up here, it is still greater than the critical angle, so it gets reflected twice. So secondary rainbow, it has two internal reflections. And then when it comes out, you have to let the engineers tell you that when you draw these with the internal reflection and knowing that the index of refraction for red light is smaller than the index of refraction for violet light, what comes out is now the violet light or the green light comes in at a bigger angle than red light. Whereas down here, the red light comes in at a greater angle, but here now it's opposite. You have to let the engineers help you to figure it out. We are not, I mean, this is not a course for engineer, not for physics, not for engineers. So, but the engineers, they will then be asked, oh, given that I have a raindrop that is now at this angle relative to the sunlight, what is the angle with which the red light comes out? What's the angle with which the blue light comes out? And what they discover when they have done all of the trigonometry here, right? When they have done all the trigonometry, ooh, the order of the angle, because it's now been doubly internally reflected, it is now opposite. That's the question. You see, for this guy, you say the angle in which the red light comes out, it is now at a higher angle with respect to a horizontal. So I see the red on top of the blue for the primary. But for secondary, it's now opposite. It has gone through two internal reflections. So instead, it is the blue that is on top and red is below. That's here. You need to work out the trigonometry with the Snell's law to figure this out. But just sort of remember or just realize that secondary rainbow, the order of the colors is always upside down, opposite. And now this is the picture. You see down here, I see the rainbow. It is red, yellow, orange, and so on. And blue is kind of hard to see. But now the secondary rainbow is the opposite. I don't know what city this is. Oh, no, this is in the suburb, right? I don't know where I downloaded this. Oh, this is from Giancoli, so Pearson. And now here, a warning. There are some, I guess, tourist agencies and so on. They like to say, hey, come to, Rio de Janeiro, I remember I saw that once. Rio de Janeiro, and you see a beautiful, rainbow. And then they show a picture of the Rio de Janeiro, the city, a view of the city with a double rainbow, right? A beautiful rainbow and a double rainbow. Except that when I looked at it, I said, ha, 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 it's fake. I mean, presumably the primary rainbow, oh, you can get it all the time. So that's easy. You get a snap of a picture of it. What they did was they photoshopped that onto another one So the secondary rainbow had also red here and blue here. And I said, that's not a true picture of a double rainbow over Rio de Janeiro. In other words, nowadays with Photoshop, with all these sophisticated, you know, devices that people have, it's sometimes easy to fool you because whoever was preparing the picture of Rio de Janeiro as one of the posters for inviting people, right? For inviting people and say, hey, you see such a spectacular view of Rio de Janeiro and so on. Sometimes they can give you fake pictures. When you now realize secondary rainbow, the order of the color has to be different, at least you will say, yeah, that is a good picture. But don't therefore fly to Rio de Janeiro on a tour just because you were so attracted by this beautiful picture of a rainbow, of a double rainbow. Okay, all right. Note the order are reversed in the secondary rainbow. Now, we need to do some, have we already done all the mirrors? Yeah, I think we have. Have we done all the spherical mirrors, convex mirrors, right? Did we? Yeah. So now we need to come to uh, another aspect of optics, which again is important for our real life. I need glasses. I don't know about you. Do you need glasses? How many people need glasses in this class of
I
28, 20?
do.
Yeah. Is it rare among your generation for people to wear glasses?
No.
No, right? A lot of people wear glasses, right? Anyway, so we need to learn something about glasses. Before we had this concave mirror, and you say, oh, you have such a lot of fun. You go through a hall of mirrors, and then you can see your sister get shrunken, as you pass by this, and you say, whoo, it's so nice and so funny, and so on. And you have the convex lens for the side view mirror because you want to see a better view of what is the cars behind you, on the side. And you need a convex mirror because you want to have a bigger field of view. But then they always tell you on the convex, the side view mirror, the car manufacturers will always say the images appear further away than they actually are because they are smaller. They are smaller, but they are not really further away. They are smaller because this mirror is a convex mirror. So we already learned about the differences between the concave and the convex and the plane mirror, right? And now maybe it's a good time do you remember Archimedes? Do you remember who is Archimedes?
Yes.
Who is he? What is he? What was he famous for in 203? You're not being tested on this, but just curious. Do you remember?
A mathematician?
Well, he's sort of a scientist, right? But what did he discover that's called Archimedes' principle? Do you remember? You don't remember this buoyancy force? For ships to float, there has to be a buoyancy force acting on this ship. Yeah? And Archimedes, he was, asked to tell whether the Macedonian princes, offer golden crown to the mighty prince of Athens, and the mighty prince of Athens sort of suspect one of those princes of Macedonia that he's a cheat, he's a fake, and in order to figure it out, he doesn't want to take the crown and then crack it to see whether it's, gold-plated or real. So he told Archimedes, you figure it out. Non-invasive procedure. And you, biomedical students, you always have to do non-invasive procedure to figure out whether there is something wrong. Well, Archimedes was given that command, and he had to then figure out, and he was taking a bath in a bathtub, and he plumped himself into the bathtub, and the water overflowed, and then he says, I found it. Eureka! Eureka! He ran through all of the streets of Athens shouting, Eureka! That you remember, right? Now, do you remember that story? Maybe your professor didn't tell that story. Yeah, okay. But now I want to say something which Archimedes is actually more useful. I mean, he is useful, but even more important for the Prince of Athens is that Archimedes was able to help defend Athens from the armada of ships, because these other Macedonians, you know, they gang up. They say, let us invade Athens. You know, we don't like this mighty Prince of Athens. We want to do something to them. And so they have an armada. They have a sort of a fleet of ships. And in those days, the ships are made of wood. Not like today. Today, the ships are made of steel, right? But in those days, these are ships that are made of wood, and they are now invading the harbor of Athens. And you know what Archimedes did? He used concave mirrors. Namely, he says, hey, all these soldiers, we have now these shields. And of course, a shield, like the Roman soldiers, those shields, they are a sort of a concave. On this side is, if you use this side, is convex, but if you use this side, is concave, right? And now the sun is over there. You now let the sun focus the rays on to the focus, right? You notice if I have the sun and they're coming in, and this is concave, if the sun ray are coming in and this is concave, they will now be focused onto the focal point. You remember? Do you remember that picture? I wish I can just draw that picture, but you remember that picture, right? With a concave mirror, if I have the sunlight all coming in parallel, they will then be focused onto the focal point. In fact, that's why you define it to be the focal point. So what Archimedes did was to say, I now know the distance from the hill around Athens, and I now have my soldiers all with these shields that have a certain curvature, and I will make the curvature just right so that the focal point is where the ships are. From my cliff here to the ship there, I now focus all of my light onto that ship. And when I have my 50, 100 of my soldiers all on the cliff, all arranging to focus onto the ship, the lead ship of this armada, you know what happened to those ships in the armada? You know what happened? I focus all of the sun's rays onto the ship in the Mediterranean. It is very sunny. In the Mediterranean, it's, you know, that's the property of around Greece. There's a lot of sun. Yes? So what happened? What do you think happened to the wooden ships? They caught fire. They caught on fire. That is the kind of using science to actually now say, hey, I make use of the fact that parallel rays coming from the sun will be focused at the focal point. And now the focal point is depending on my curvature. And of course, I can now curve it in just the right way. So I focus it on that armada coming in. So he will tell the soldiers, focus on the first lead ship. And when they all focus on the lead ship, it catches fire. Now, next, focus on the second ship. Next, focus on the third ship. And that's how they actually won the battle. And that is more important to the mighty prince of Athens than Archimedes' principle. But for us, of course, Archimedes' principle is very important because we all need that for the applications like you have cruise ships. You want to go on a ship, you want to cruise a cruise ship, you need this buoyancy force. Okay, anyway, I now come to lenses, which is another aspect of optics. And again, there is converging lens, there is diverging lens. You know, like for the mirror, there was a concave mirror and convex mirror. And lenses will also perform this refraction and direct a ray to some focal point. With a converging lens, paraxial means rays that are parallel to the axis, all right? Paraxial rays, rays that are parallel to the principal axis, converge to a focal point. This is now a lens. Archimedes did not use a lens because a lens would be too complicated to immediately manufacture for this invading armada. Instead, he was using a shield, a concave metal shield as a mirror. Well, so now if you have a ordinary kind of, prism or arrangement, parallel rays, they will be bent through the prism, and it will be sort of like a, no focal point at all. This is not yet a lens. A lens now, it says, I am now going to shape my prism. I'm going to shape my my glass, right? But I now shape it in a curve. Now I shape it in a curve. And the engineers, they actually do a lot of research on how to shape it. And you have all the optical companies, they have patent rights on how and what to do to shape it. And there are many issues involved in that, but we are not interested in that. All we are interested is from the user point of view. We say, can you design, namely shape this prism, right, glass, shape it in just a right way, and it should be a thin one. You don't want a converging lens that is, 6 inches thick. I don't want to wear a glass that is so thick. I want to wear a glass that is very thin, and then you pay for all the frame. It is elegant and so on. So you then say, I want you, whatever optics company you work for, design a lens such that when I have these rays coming in parallel, that they will all be focused at a single point. This then is called the focal length, and the notation for it is little f. It's the focal length, because all of this light will now be converged onto this point. With a diverging lens, it's now the opposite. You want it such that it will be diverging away, such that rays that are parallel to the axis, the principal axis, they call it the principal axis, that it will now all be diverging from it, such that it is as if it came from a focal point, but it's a virtual focal point. You see the difference? Converging lens, it's a real focal point. The light actually did go through this focal point. But now for a diverging lens, it is coming from a virtual focus. And then the engineers will now say that this focal length is negative. They use a certain convention. When it is a real image, a real focus point, then it is a positive number. But when it is virtual, they will call it a negative number. All right? I mean, that's just like a sign convention. But it is easy to appreciate, to grasp the concept that a converging lens converges the rays, a diverging lens diverges the rays. And then they call it double convex, plano convex, convex meniscus. I'm not a optical industry guy, so let them design all the various advantages of a double concave versus one side plane, one side. These all have to do with the internal path of the light. But for us, we just want to now get some understanding of this imaging with the lens. I have a converging lens, and I guess they will call this a double convex lens, whatever they call it. Anyway, there is this converging lens that they have designed and produced and that I have paid money for. And what I want is, I want to now say, what is the image that I have due to this lens of an object? I place this object over here at a distance that is beyond the focal point. If I put this object over here, this object will send rays. One ray that it will send is a ray that is parallel to the axis. And when it comes in parallel to the axis, the manufacturer of this lens says it will be bent towards the focal point. So therefore, this ray will now go like this. All right, so that is the first ray. I'm drawing what they call ray diagrams. And then next, I have my the same object, the top of it, sends a second ray, which is going through the focal point, F. When it goes through, it will now go on to this ray and be coming out parallel to the axis. So then this is the second ray. And then third one is if I have a ray that comes from this top of this object and it is directly at the lens itself, it goes through the center. If it goes through the center, it just goes straight through. Well, if you now put all three together, well, this is the opposite for diverging. You have now this diverging lens. It will now, when you have the first ray that was parallel to the axis, it will be diverging away. And if you now have the second one that is focused on the focal point, it will then come out parallel to the axis. And the other one that goes through the center of the lens, it will just go straight through. And you can now see the image. If you have this object here, and you go through the three rays, one ray is parallel to the axis, it will go through the focal point. The other ray go through this side of the lens, it will then come out parallel. And this third one goes right through the center of it, will come out. Therefore, it will appear as if they were focused on, the ray from here is focused over here. So this now is the real image because the light actually did go through it. But the real image now is smaller and inverted. Right? This is just the kind of application of a converging lens, that the converging lens gives you, for an object that is far away, further than twice the focal length, for an object that is far away, the converging lens will produce an image which is real but upside down. All right, I mean, this is just being able to draw what they call ray diagrams so that you know. Now, for you and me, most of the time we don't care about this. Most of the time we are more caring about how does that help my eyesight. And later on, towards the end of this chapter, we will come to the human eye, because I think that's important. Even if you are not going to be an optician, You are going to be wearing glasses like you and me, and we will be interested in these issues. Okay, but for the moment, let's just follow the book. When the object is placed further than twice the focal length, the real image is inverted and smaller than the object. And that's what is used in a camera. Nowadays, few people buy a camera. This is what they call a single lens reflex camera. There are some cameras that are double lens, and there are even more complicated ones for these professional photographers. But this is a what you call SLR, single lens reflex camera. And what it is a converging lens. Of course, the camera manufacturers, they charge you a lot for this lens, because this lens has to have not just the simple property of producing an image that is down and inverted, but it has to be no spherical aberration, no chromatic aberration. In other words, there are no additional color, fringes to my image. If I snap a picture of you in front of Empire State, I don't want to see your face with a rainbow around your face and so on. That would be terrible. And we all know that there is some color, because index of refraction going through this lens, there is a difference between red and blue and green. And the camera manufacturers, they have to minimize. They have to do it such that when you take a picture, it's your beautiful face, the beautiful Empire State. No additional fringes, coloring, red and blue and green around your face. Please, no, I didn't pay you $300 for a camera to have those, distortions. So this is simply the basic aspect of converging lens, but the camera people, they spend a lot of technique in polishing their lens so that it does not give you that kind of spherical aberration. We'll see that example, and chromatic, namely the dispersion. And now, what if, you see, previously you put it far away, but supposing you didn't put the object far away, but you put it closer now, and you do the same analysis. You see what we are doing now. The previous one, you put it far away, and then you say, whoa, I now find that the image is real and it is inverted. But now what happens? The book just sort of says, you'll be curious to know what happens if I, instead of putting it that much farther away, I put it now closer, between twice the focal length and f. If I put it there and I go do the same elementary exercise, and I say, I draw a parallel ray, it will go through the focal point. I draw a ray that goes through this side, the focal point, it will then come up parallel. And if I go through the center of the lens, it will go straight through. And voila, I now find that it will be a real image, but it is bigger. This image here is bigger than this. I mean, this is geometry. Well, trigonometry, geometry. This is just drawing the geometric rays, and then we discover, oh, the image of an object that is now closer is still inverted, but now it is magnified. When the object is placed between f and 2f, the real image is inverted and larger than the object. And lo and behold, the engineers, they actually make use of that. How? Because you have a projector, you want to project onto the screen. So clearly you want to have a image that is large, right? And you want it to be a real image that is large. So what do you do? Oh, you have the object upside down. I mean, that's what the projector, the film, the way they roll the film through the projector, they have it actually inside upside down, but small. And then they have the light projected. And so then what you end up with is, ooh, a nice, movie screen. Do you see now how these simple things can actually have real life applications that you enjoy? You may not realize it, but that's what the movie projector does. But that's all inside. Nobody would actually, if you were working for a cinema, you wouldn't actually, your owner would not let you break out the projector inside to say, oh, which way is the film rolling, and is the film rolling with the actual images upside up, right side up, upside down. In order to project over here, these themselves have to be oriented upside down, and the film just goes, in a reel in that way. All right. So the application of these light ray, of these optics for a converging lens has applications in many of our applications, real applications. Any questions or comments here? And now, since we're on this thing, it might be good to remind ourselves, because after all, you have learned about polarization. Do you remember which chapter was it with polarization? I forgot. Which chapter was it that had polarization? Is it 24? Is it 25? Let me see. Which chapter was it that had polarization? I think 20. Is it 20? 24, I think, right? Anyway, that's your that's your own, you are younger than me. I get all confused between 24, 25, 26, 27. Anyway, you remember in an IMAX, they actually have a projector that has two images superposed, because when they first take the shot live of, let's say, this eagle flying towards the camera, they have the Polaroid filter on the left that is different orientation than the Polaroid filter on the right. And then the image rays now get onto this film. This film is still a single film because you are recording it all on this film. So you're recording the left and the right image on this film. It's not that there are two different films. It is just one film on which you have recorded the left and the right image. Now, when they put it into this IMAX projector, then this film image now comes out and goes onto the screen. And the screen, what you see on the screen, if you do not wear the 3D glasses, what you see is a blurry mix of images, so that you don't see me, you see a double image of me, one slightly shifted from the other, one with more red in it and one with more green in it or whatever, so that what you see is simply something that you say, forget it. Why did I pay $10, $15 for this? But when you put in your Polaroid glasses, then the same image that you now see now comes through this left-hand glass, which now has that Polaroid filter, just like the original camera lens for the left, so that the image that comes to your left eye is what the left lens of the movie camera saw. And then this image that you see on the right eye, because the Polaroid filter now is the orthogonal one, it will now only pick out the image according to the polarization. Therefore, it now comes to your eye like as if you were there. And that's how you have this IMAX, where you see a big screen and you now are able to see the left and what the left eye and what the right eye sees, and you say, wow, this eagle is coming straight towards me, trying to grab me. All right. Okay. But now, since they have already started out with this converging lens very far away, and now in between twice the focal length and the f, now they want to put it even closer. Now you want to have this even closer within this focal length. And now you draw the lens, the rays. Well, if you draw a ray which is parallel to the axis, it will then be bent towards the focal point. So that would be this ray. But now the ray that comes straight through the middle of the lens is undeviated. It comes straight through. But now what you see is a virtual image. So remember, when it was very far away, it's real, inverted, but smaller. Then you come a little closer, it is still inverted, but now bigger. But now if you come closer than that, boom, it becomes virtual. But virtual, but bigger. And that is this converging lens. When the object is placed between F and this lens, the virtual image is upright and larger than the object. And now, that's what the magnifying glass is. Do you realize that's what you use? I guess when you become a doctor, do you need to look at people with a magnifying glass? Do doctors and nurses use these magnifying glass? No? Hmm. I guess, why? You don't care? You don't care to see whether, I guess a dentist would use it, no? Would the dentist not want to know whether there are things between your teeth to see whether there's a lot of dirt in there? Huh? Yeah. So magnifying glass is very useful. And nowadays I need a magnifying glass to look at some of these pictures because they are too blurry for me. So I need to magnify it. You see, so it is a very useful optometrics. Yeah, that's right. Optometrists, they do that, right? Yeah. So there are all these applications, all just by using this simple thing called the converging lens. But there's a lot of technical things that the people have to do because, as I said, they don't want to have the rainbow colors around it. I don't want to have, when I look, I see all the E, but E has, rainbow diffraction. We will learn in chapter 27 about diffraction, that there are all these, dispersion of the color coming in. You want to see what it was. So that's technical thing, which they have solved and they charge you for it. Now that we have done all of converging lens, let's now go on to diverging lens. And we can again now first take, for a diverging lens, you first take an object that is further away than the focal point of this diverging lens, all right? And you now say, okay, I know when it is a parallel ray coming in, a diverging lens, it actually diverges, goes up. But now a parallel ray, not a parallel ray, a ray that is at the center of this lens just goes through undeviated. Therefore, when I'm on this side of the lens, what I see is now a virtual image, because this light seems to have come from a virtual image. So this now is the virtual image, but this virtual image is smaller than the original. All right. So this is now the property of a diverging lens. The diverging lens always, it actually does not matter whether you have it here or how far away, always forms an upright, virtual, diminished, namely shrunken image. And this is a separate, I never use this. I don't know, do optometrists use this? I don't know who would use this. Can you imagine anybody who want to make a image smaller? Can somebody suggest a use for it? A diverging lens like this? Huh? I don't know. Maybe someone can have a clever use for that in some application. The book doesn't tell you. I am not in that industry, but that's what the property of a diverging lens is. And yet, a diverging lens is important for us. We will see how a diverging lens is important, how a converging lens is important for people with eyesight problems, nearsightedness and farsightedness. Okay, so now we just need to summarize the engineers. They have already spent all of their life, developing these lenses and so on, but now they want to have a simple formula. It's called the lens formula, thin lens equation, because this only works for thin lens. For a big, thick lens, oh, it's much more complicated. And they spend a lot of money and patenting the rights to a thick lens. But for a thin lens, all that matters is you need to tell me the focal length of this lens, of this converging lens. It's positive. And you now tell me you place the object somewhere, and you will call it d sub 0. Right? So this is the distance of this object from your lens. Call it d sub 0. 0 does not mean initial. This 0 means object distance. You have your object distance, d object, and then the image will now be formed. And if it is real, it is positive, di, d image. All right. This is d object. It's in front of this lens. It's the object, and it is positive because it's in front of this lens. And then the image is always behind, and it's real, so it is positive, the image. And the focal length is f. For a converging lens is positive. And voila, they have discovered that 1 over d object plus 1 over di is 1 over f. So it's sort of like the Snell's law. N1 sine theta 1 equal to N2 sine theta 2. But this is valid only for thin lens. But it's a very convenient law that applies to all situations. So that is this law, right? It's called thin lens equation. And you would also be interested, because you are spending a lot of money manufacturing these converging lens, diverging lens. You want to ask, what is the image relative to the size of the original. Is it magnified? Is it shrunken? So there is this magnification. And the magnification is now, what is the height? You have original object, it has a certain height, and now the image, if the image is inverted, this one is actually negative. If the image is still up, then it is positive. This is my original object height. And now in this case, the way that they have applied it for this particular lens, the image is now downward, so it's negative. And how is it? Well, it is negative di, the image distance, over the object. And this image distance is real because this is a real image, so it's positive. So magnification is minus, meaning that it's inverted. In other words, the lens equation has all of the aspects of my lens, how far away, how close, etc., whether it is real, whether it's inverted, whether it is virtual. All of those are summarized in one single equation with algebraic convention. You got to give them credit that they have indeed been able to find a single simple thin lens equation that summarizes all the funny things that converging lens, diverging lens can do for your camera, for your projector, for your eyeglasses. All right. So just to emphasize that this equation is a very useful, even to an optometrist, even to, I don't know about ophthalmologists, but anyway, all the applications, all the cameras and sophisticated microscopes, they indeed make use of this overall formula. And then the sign convention, for converging lens, the focal length is positive. For diverging lens, it's negative because always the image comes from a virtual focal point. And the object is, if you are to the left of the lens, it's positive. And it would be, if it is placed to the right of the lens, it's negative, just a sign convention. And image is formed to the right, then it is positive. If image is formed to the left, it's negative. And magnification is positive, right, and negative for inverted. And so this is just sort of like a simple application. They say a 1.7 meter tall person is standing 2.5 meters in front of a camera. The camera uses a converging lens whose focal length is 0.0500 meters. Find the image distance. Well, the image distance by using this formula is 1 over f minus 1 over d object. And you just plug in. You say, well, I am told that the focal length is 0.05. And then I'm told that this object was 2.5 in front of the camera. And so you put in the algebra and it comes out to be 19.6 inverse meter. Therefore, the image distance is 0.05. So the image is real, right? Because the number turns out to be positive. So by algebraic convention, this image is real image. And then next you say, what is the magnification? Well, magnification is now negative minus di over d0, I mean the object, and we have already worked out that di is 0.05, and we know that the object was 2.5 meters away from in front of the camera. Therefore, this one is now inverted and it is shrunken. So the height of the image is, therefore, you can now figure out, is inverted and it is 0.0347. The person himself is 1.7 meters, but inside the camera, the image is 0.0347 meters. And the engineers, the manufacturer of the single lens reflex, they have already made use of all of that in order that you can, all you need to do is to focus and you snap. All right. Okay, so maybe we will stop here. And now let me just again quickly summarize what the test would be. It is, yeah, the exam, let me again look at my, the exam is on chapters 21, 22, 24, 25. And now since there are only 15 questions there won't be, I cannot say, oh, all the topics covered in chapter 21, 22, 24, 25 will be included in this test too. I will have to pick out some things from 21, pick out some things from 22, pick out some things from 24 and from 25. So it will not be like, you know, I will have covering all the topics. And you can use your notes because you have your whole laptop and you have all of the access to all the PowerPoint that for all the different chapters. So you have all of that available. And as I keep emphasizing, whenever you take a question, you ask yourself, what is the concept that is involved? Is the concept the question that involves the magnetic field around a wire carrying a certain current, I? If I know I, the current flowing in the whatever circuit that you have, do I then now know what is the magnetic field around it? And what is the somebody's law? I forgot. Is it Hooke's law? Is it Newton's law that tells you what is the magnetic field? If I have my wire going with a certain current I, do I know which way is the magnetic field? Which way is it going? You know, clockwise, counterclockwise, relative to this, right? You need to know your hand, your right hand rule, right? So if I tell you that this is a wire that carries a current I, so many amp, milliamp, or whatever unit I use, then you will know the direction of the magnetic field around it and its dependence on the distance away from this wire. Far away, the magnetic fields would be smaller. Close, the magnetic field will be bigger. How much bigger? I forgot. You will look up the formula for it. And then you will be able to now apply it and use it and say, ooh, therefore I know now what is the force on this wire due to somebody external magnetic field. What I spoke about here was magnetic field due to the wire. But you also have to be careful. Sometimes the question is not what is the magnetic field due to the wire, but magnetic field due to that is fixed on you, applied upon you because you have a magnet on my wire. You have a magnet, North Pole, South Pole. You have a magnet that now is influencing my current. And if that is the case, I am not using Ampere's law, somebody's law. I'm not using somebody's law. I now have to use a different concept, which is what is the force on this wire due to the magnetic field you impose on me. You bring a big magnet and you now make a big magnetic field, applied magnetic field onto me. And I am the current that's flowing. Well, is there now a force on me? Is there now an EMF induced as a result? So you have to ask yourself, is this a question involving EMF? And if it is a question involving EMF, is this what the book wants to distinguish? Motional EMF. You remember this thing about motional EMF? Due to the fact that there is a motion of your wire, your rod, moving in a certain direction through a given applied magnetic field, there is motional EMF. What is it? I don't know. You remember the formula. You look up the formula. And then when you know that this question involves motional EMF, oh, then you know which formula to use. All right. And as I said earlier, if this is a problem that somehow seems to be related to Faraday, well, there is also the induced EMF. Induced EMF due to the fact that your circuit, your loop, your whatever shape loop you have, in fact, now moving through a given magnetic field, and so that the flux through that loop is different now, changing. If that is so, then I guess it is somebody's law that you have to use. And then you say, oh, now that I know it is something that involves, somebody's law, I look up that formula, and then I will now plug it in to figure out what you have told me. All right. So always ask yourself, what is being, what's the concept involved? Is the concept electromagnetic wave? Is the concept the velocity of light and the relationship between the wavelength and when you have the amount of light coming from the sun? You remember there was some amount of energy coming from the sun, and there is this thing called the intensity. You remember? And it is when it reaches the Earth upper atmosphere, it's about 1300 and what is it, 1340 or 1370 watts per meter squared. So when it arrives at the top of the Earth's atmosphere, the sun's energy coming in, impacting on the Earth is 13, I don't know, 70 or 40, whatever, watts per meter squared. But by the time it comes down to us on the surface, it's no longer 1300 something, it is less, maybe about 1010, something like that, watt per meter squared. But that is the actual energy that you can use. And now if you were Archimedes, and you now want to focus it onto your armada, space, somebody's ship, you will then say, I want to now focus all of this 1070,000 something watt per meter squared, focus it onto the focal point. Yes. And I want to focus it onto the focal point. And then the question is, how much energy is in the focal point? Now you got to think about that. So it is something that you can now say, oh, I know this is the amount of energy. And now all of that energy is put into this focal point. How much is this energy? I don't know. You need your trigonometry. You need your skill now. You got the concept. You need your skill. So be aware of that and spend time looking at the question and then plunge in. Don't plunge in right away. Oops. All right, are there any questions? Yeah. Are there any questions? Can somebody read that out?
To clarify, there will only be general questions asked from chapter 25, correct, by Gujarat.
Chapter 25 was what? Just remind me, it's just what? Plane reflections, right? Mirror. That's very easy. Nothing concave. It's just plain mirror, right? Chapter 25? What was chapter 25? Reflections, yeah. So I don't know. I have not yet finished setting up the exam. So, but that is really, I would consider that so easy that, I mean, easy in the sense that it's so easy for me, but it should also be easy for you. You don't have to sort of learn all these things about concave mirror, convex mirror, and so on. So in a way, chapter 25 is easy. It is chapter 22 and 21 and 24 that is more tricky, yeah. Any other questions?
Professor,
Yes.
you had said that you were adding 40 points to our exam one score,
Yeah,
but
that's the raw score.
I only
Yeah.
got 30 added to my raw score. So I'm wondering if that was a mistake because I'm trying to decide if I want to keep that grade. And I think that really comes down to whether or not I get 40
Well, I
points
better,
added versus 30.
yeah, okay. I will look into it. I mean, for those things, you better send me a separate email
Yeah,
because
that's
then I
fine.
have
I
to.
can send you an email. Yeah, sure. I just
Yeah,
wanted to
yeah,
clarify.
remind me because I I would not remember all these things. Right?
Yeah, I
All I
understand.
know is raw score for exam one, for test one, includes this 40 points. So everybody got the 40 points.
Okay, because I mean, yeah, I understand, but I definitely only get 30. So I will send you an email
Okay, let me
right
check.
now.
Let me check.
Okay, all right, I
Okay.
appreciate that. Thank you, sir.
Yeah. Any other questions?
Professor,
Yes.
do we have to email you if we don't want to keep the first exam, or just if we do want to keep
No,
the
no.
first?
If you don't, then I will not highlight it on my grade on my spreadsheet.
Okay, so
Okay,
unless we want to keep it, then we email you, correct?
that's right. You
Thank
want to opt in, you tell me. If not, it will not be counted in, and so it would be depending on what you do, test two and test three. Yes.
Okay, thank you so much. Have a good night.
Okay. Say, have a good rest and stay safe. Yeah. Any other? Okay, I will now stop the recording.